Assalamu alaikum viewers, this is Akhtar Ahmad Sufi presenting you with our first lecture video on Quaternion Groups. As we are already familiar about a group structure, a group is essentially a set along with a binary operation which satisfies a group checklist. That is, a set G along with a binary operation star is said to be a group if it satisfies number first closure property, that is the composition of any two elements of G under this operation star is again in G, that is for all A B belonging to G implies A star B should also in G. Number second, it should satisfy associative property as well. And how does the associative property look like? So we say for any three elements of G, those elements may be same or they may be distinct. For any three elements A, B and C in G, if we have A star, B star, C is same as A star, B star, C, while in the first case we are evaluating these two and in the later case we are evaluating these two. In fact, this has to be valid for every element of G. And number third, if there exists an identity element in G. Now how does an identity element look like? Say we say an element E is said to be identity element in G under this operation star if A is any element of G and E is operated upon A, then we have A star E is same as A, that is E is said to be identity element when E is operated upon A, leaves A unchanged. Now it is synonymous if we operate pre or post with A. Number fourth, there should exist inverse for each element. So an element B is said to be inverse of A. An element B is said to be inverse of an element A in G if A star B gives the identity element. So a set G along with these four binary operations, along with this binary operation, if it satisfies these four properties, closure property, associative property, identity property and inverse property, then we say the group, a set is a group along with that binary operation. Now, as the word Quaternion group suggests, so it essentially has to be a group. So that means it has to be a set along with a binary operation. Now, what type of set is this? So if we define a set as plus minus 1, plus minus I, plus minus j and plus minus k. So that means Q has 8 elements, so we denote it as Q8. So it essentially means Q is a finite set with 8 elements. Now these I, J and K's, they behave as complex numbers. Say we know for complex numbers we have, iota is equal to under root of minus 1, iota square is equal to minus 1, iota cube is equal to minus iota, and iota raised power 4 is equal to 1. And similar procedure occurs for J and K. Now what kind of binary operation is defined on this set? So if we define the binary operation on this set as I dot j is equal to k, j dot k is equal to I, and k dot I is equal to j, the binary composition in Q looks same as the vector dot product. So we know the vector, in case of vector dot product, say we write I, j and k, I, j, k. So if we move in the clockwise direction, we take I dot j as k, j dot k as I, k dot I as j. But when we move in the anti-clockwise direction, we take j dot I is equal to minus times k, I dot k is equal to minus times j. So this is how we define the binary operation in this set. Say we have defined I dot j is equal to k when we are moving in the clockwise direction. When we are moving in the anti-clockwise direction, we are defining j dot I is equal to minus k. So this is the set Q8 along with this binary operation. Now in order to show that it is a group, we have to show it satisfies those checklists among the group structure. That is, we have to show it satisfies closure property, it satisfies associative property, it satisfies, it has an identity element, and every element has inverse. Now number first we will be showing it satisfies closure property. For closure property, we have to see all the elements of Q8 under this binary operation or again in Q8. So this means if we put on any two elements of this I Q8 plus minus 1 plus minus I plus minus j plus minus k and have the binary operation defined in this sense, and that should be again in Q8. So what does this mean? So if we have, say, if we verify this result, so we can simply write the verification here. So as we are dealing with few elements, we can write the verification here. So if we take 1 into I, what will be 1 into I? So it will be I, which is clearly in Q8. Now if we take any two different elements, say I dot j, what will be I dot j? As per this, I dot j will be k, and k is again in Q8. Similarly, we can prove for other elements as well. So we say composition of any two elements of Q8 is again in Q8. That means closure property is satisfied. Now moving on to associative property. Now in order to verify the associative property, if we can again have the verification as well. If we take any three elements A, B and C in Q8, where A, B, C are among plus minus 1, plus minus I, plus minus j and plus minus k. We can take any three elements among these. Now we simply had to show A, B, C is same as A into B, C. Now if we again verify this, we can take 1 into jk, 1 into jk. So we have to show this is same as 1 into j into k. Now we can say 1 into jk, so it will be j into k. What will be j into k? It will be I, so this will be I. Now this I jk, 1 into j, so that will be j into k, so j into k, it will be again I, which means I into j into k same as ij into k. Now if we take I, j, k, these elements, so it was 1 jk and here we were evaluating 1 jk. If we verify the result for I, j and k, then we have to show I, j into k is same as I dot j dot k. Now what will be I into j? As per this, I dot j will be k, so this will be k into k, which means it will be k square. Since k behaves as a complex number, so it will be k square, it will be minus 1. Now I dot jk, what will be jk gives I, so it will be I. And what will be I into I? It will be I square, and I square is again minus 1. So I dot j dot k will be minus 1, and this I dot j dot k will be again minus 1. So which means the associative property is also satisfied as well. Now if we see whether it has an identity element. Now moving on to identity property, we have to see whether there exists any element in Q8 which when multiplied with any element of Q8 leaves that element unchanged. So we can write clearly 1 belongs to Q8 such that 1 into 1 gives 1, 1 into I gives I, 1 into j gives j, and 1 into k gives k. And similarly for minus 1, minus I, minus j and minus k, which means 1 is the identity element, because when 1 is multiplied with any element under this binary operation, that element is left unchanged. So 1 is the identity existence of inverse. We have to see whether each element in Q8 has inverse element. Now we can write 1 into 1 is equal to 1, which means this one when multiplied with this one gives 1, which is the identity element, which means 1 is inverse of 1. Minus 1 into minus 1 will be 1, which means this minus 1 when multiplied with minus 1 gives identity element, that is minus 1 is inverse of minus 1. Now iota into minus iota, we are having this binary operation. Iota into minus iota, this will be minus iota square, and minus, this will be minus iota square is minus 1, so this will be 1, which means minus iota is inverse of iota, and minus iota is inverse of minus iota. Again, j into minus j will be, this will be again 1, which means minus j is inverse of j, and j is inverse of minus j. So similarly, k into minus k is equal to 1, which means minus k is inverse of k. So which means this Q8 is a group because it satisfies all those properties for being a group. Now in addition, if it satisfies the commutative property, then this will be called a abelian group. Now if we see I dot j, what will be I dot j? I dot j, it will be k, and what will be j dot I? J dot I, that will be minus k, which means I dot j is not equal to j dot I. So commutative property is not satisfied. So we can say this is non-abelian group. In fact, Q8 or the Quaternion group is one such special group, such that the group is itself non-abelian, but it is proper all of its proper subgroups are abelian. The group is itself non-cyclic, but all of its proper subgroups are cyclic. In fact, all of its proper subgroups are normal as well. We hope this video is helpful to you. So we'll be back with Quaternion rings or Hamiltonian rings, but for that you have to like, share and subscribe our channel, and do not forget to hit the bell icon to get the earlier notifications. Thank you.